Thank you guys for having us today. I have been using AnyLogic for quite a while, so it's great to be at the conference and see the product and the conference growing over the years. I'm not going to spend a lot of time introducing Mosum Tech because my coworker Jeff Brailsford is going to talk a little bit about our company later. I just want to introduce our presentation because we've actually got two projects in one presentation. John and I met at the AnyLogic conference in Philadelphia, which I believe was about 3 or 4 years ago.
2015.
2015. And several months later, we got a call from Walmart saying they needed someone to evaluate John's technology because we didn't quite know if those spreadsheets could be trusted. And John even admitted there are some areas in Excel that weren't quite adequate, and we could really get into a simulation model and more fully evaluate the technology. So this was 3 years ago. Mosum Tech came in, and we had 7 weeks to help Walmart make a go, no-go decision on this grocery technology. And then after that, Christian took over the model and has since been adding more and more details to it, advancing the model, turning it into a true engineering design tool. So I'll cover the first project phase that we did 3 years ago, and Christian will get into the more recent details. But John's gonna take you guys through just the technology.
I describe myself first as an inventor and now as an entrepreneur. As an inventor, I got interested in supermarkets in the mid-90s as an opportunity for innovation. And I started envisioning a supermarket, a store in which robots or automation, I didn't know that the robots at the time would fill orders automatically for customers, eliminating the need for humans, the customers, to walk up and down the center aisles of the center store aisles in a supermarket, which would work really well for packaged goods. But as a customer, I want to be able to pick my own peaches. I don't look for the best looking box of cereal, but I do look for the best tomatoes, the no bruises, and so forth. One's not the same as another. So I want the system, this is a thought experiment at what would be the perfect store for a customer. And it would be one in which I could have machines pick the orders that I don't care about picking the individual product, but let me have the choice. But I also want to be able to order those online too. This was before the internet, but I was imagining catalog software on my PC that would phone over a modem and have the order ready for me when I arrived at the store. This idea sort of took over my life, and I couldn't, because what I realized was that with an adequate automation system, it would be more profitable for the retailer as well. The problem that I discovered when I started actually looking at automation solutions is that it was totally impossible, wasn't even close, would require something far more advanced than existed at the time. I couldn't let go. I decided that this was worth putting effort into. If I could solve this problem, it could change retail. And so I started working in automation, and I'm not going to give you or put you through the pain of joining my journey over the next 20 years, but I'll just jump forward to 2015. I was working with a co-founder and co-inventor, Bill Posnight, and we came up with this design solution. If you look in the just behind the decks where the robots are moving in 2 dimensions, you'll see the robots can go up and down. So the breakthrough in this design is a robot that can not only act as a 2-dimensional mobile robot, but can position itself at certain locations in the structure that we call towers and actually engage a pinion gear and elevate itself up and down. And so it can move to any storage or workstation elevation in the system. And this breakthrough allows us to eliminate all conveyors and all lifts and have the only moving part in the storage and retrieval system is the robot. We had another moving part at the workstation, but you can see that the robots are actually the mechanism that moves through the workstation. Because it can move vertically, it can elevate and present to the picker. So we have robots that are bringing products to the pick station. Another robot brings an order container, and the picker is transferring the products to the order, from the product containers to the order containers. And this is the solution that lets us put a robotic material handling system into the center store of existing supermarkets. And this was the concept that we presented to Walmart. Walmart was looking for a solution to be able to automate online fulfillment at store level And we showed them this, and they got very excited about it. And they wanted to build a tool to evaluate it because they didn't, as Amy said, they didn't trust my spreadsheets, and neither did I. So I gave the reference to Mosentech to bring them in as the solution partner because I wanted to use AnyLogic, and I convinced them that if we built the tool in AnyLogic that we could preserve the value of that tool by extending its capability and making it an engineering support tool, and that's what we've done. So we brought Christian and Bill. We hired a great team. We have just an amazing team. We've developed this technology in record time of two years. We're now piloting at a super center in Salem, New Hampshire. Christian is part of our team, so he became the simulation engineer, and we've used it as Christian will describe. So this is the addition onto the Supercenter in Salem, New Hampshire. You can see the cars come and park. These are images of our system inside the facility. And this next video is a composite video showing what life looks like to an AlphaBot inside the system. The lower left hand is a stationary camera. You can see them moving on the decks between the storage aisle they're coming out of, and they're going into workstations. The other images are images from cameras. We've got 6 embedded cameras in the robot. A lot of these images were from a 360-degree camera so we can pan and show. So this is what the system looks like in operation. And then I'll turn it over to Christian I'm sorry.
It's okay.
To Amy to talk about the kickoff.
Thanks, John. I'll go through the phase 1 very quickly. As we mentioned, Walmart needed to make a go, no-go decision, and this moved very quickly. I think we got a call on a Tuesday from a Walmart executive, and they asked us if we could be in Boston on Monday. And so I think from that point until we needed to come back and give final results, we had 7 weeks for specification, model development, testing, analysis, developing a report. So we had to move very, very quickly. One of the things Walmart really wanted was a tool that was flexible enough to handle multiple sizes of stores and customer bases, which was a really strong positive for AnyLogic because we do feel like it's one of the best tools out there in terms of runtime flexibility. And Walmart wanted that not just because they wanted to look at their current, what's my immediate question, but eventually as this tool continued to grow, they knew it could be used for sizing future stores and determining which markets were most attractive for an AlphaBot system. One of our unique challenges was, the system didn't exist yet, which structurally we could think in terms of, how high are the racks, how wide are the aisles, but the control logic didn't exist. So when an order comes in and we have multiple bots, who gets it? How do we prioritize orders? How far ahead do we call orders so those loaders are staying busy without creating too much congestion? So we had a lot of whiteboarding exercises to say, well, what would that level of control logic look like? We did avoid, however, the detailed congestion modeling, which I believe is what a lot of Christian's follow-on work was about. We took the approach of let's be pessimistic, let's assume one robot in an aisle at a time so we don't have to worry about collisions. And we knew that would be pessimistic because we didn't want to overpromise Walmart anything that the system couldn't actually do. So in terms of inputs, they had complete flexibility to define their demand, whether that would be lines per order or eaches per line. The bots themselves, we could look at their speeds, acceleration, deceleration. We have this concept of a speed derating factor. There was one area of the system where bots were traveling, and we knew there could be some congestion factors, but we simply did not have the time to build out that detailed collision avoidance logic. So while my partner, Sarab, was building the main model, I built a side model using the road library, where we could kind of mimic what we thought this area might eventually look like, and we developed a congestion to speed derating curve to eventually feed back into the main model. And I think the other input that's unique about this one is simply the fact that they could go in, they could change the number of tiers, the number of aisles, how deep the aisles were. They could change all the physical components of this system. So just a quick demo of that phase 1 model where they could come in, change their things in Excel, hit the run button. A very, very simple dashboard came up. We did eventually have to add a basic 3D animation. There was some concern that this looked so simple, people would think it was just an Excel spreadsheet. So we did have to put the 3D animation in there, but as you can tell, it's pretty basic. But what is nice is this animation would scale. If they said, I want 10 aisles or 4 aisles, they could physically see in the animation that it would scale appropriately to what they put in. And then once the model is done running, we'd get the outputs back into Excel where they could look at detailed log files, summary tables, or charts and graphs. When we were running our real analysis, we had another mode of running this where we would launch off huge batch runs and get summary files so we could do more detailed scenario analysis. This is one of our summary slides that was shared with Walmart. And you can see I have a quote from last summer that showed up in Yahoo Finance. And I was tickled to death to just see this come across my LinkedIn feed, that they were quoting the computer simulation models. But the slide in the background, these were our original predictions, that 95% of orders can be picked in under 8 minutes. I was recently telling some of my girlfriends about this technology, and they said, well, that'll never work. I'd have to have my order in 5 minutes. And I said, you can. The average time was actually under 5 minutes. And then the quote from Yahoo shows that the newer simulations are showing average pick times of 3 to 4 minutes, and I believe that's because Christian and the team have been optimizing all of that control logic and optimizing those collision avoidance logic. So the original model was pretty accurate, but they have been able to continue to squeeze the system to get it even faster.
Thank you, Amy. As both of them have pointed out, we're still using the model that was implemented in the 7-week rush at that time. But the focus and the purpose of the model have changed quite a lot. As you can imagine, evolving such a model over more than 2 years, there isn't much that's still left in the model as it was before. But still, it was great to start from a running model and just be able to increase the level of detail of certain aspects as it was necessary throughout the development. So we're not looking at the binary decision that Mosentech was looking at before, but at a supporting tool for the actual development and design of the system. So starting from the actual model, as you've seen before, we needed to put in more specific logic for the bots moving, the bots reserving their paths in the system to avoid collisions of the bots, including movement profiles done in a conjunction between built-in AnyLogic agents and own Java functions to be able to also include acceleration and deceleration, for example. We're separating temperature zones, and most recently we've put in the inventory tracking. So the model is now able to actually track every each that is put into the system and picked into an order and taken out of the system again. So just to give you a comparison to the of the model, come on, yeah, here we go. The model, what it looks like today. So as you can see, it's quite a complex model in the meantime. You can see bots of different colors moving around that are doing different kinds of tasks. Planning that path as indicated by the colored lines, reserving points on that path indicated by the dots on the lines, So as a big complex thing, it sometimes looks like a 3D Pac-Man game as the bots eat up their dots. You can also see the bots temporarily parking on the decks. So we've also included the sorting on the decks, so to make sure the eggs are the last thing that's put into the order bags at the end, so we don't crush them. We had a little concern about the performance degradation that might come from that specific aspect, but so far it turned out that it doesn't really impact the performance or it's rather negligible. So just to give you a few examples of what we've used the model so far, obviously to design certain layout alternatives for specific locations, but for the whole development process, it was extremely valuable to have the model ready as a support tool for certain development decisions. Obviously, there were specifications in the beginning for things like bot speeds in certain areas. But when you go through development, some specs turn out to be achievable pretty easy. Others are pretty hard to achieve. So we always use the simulation to see how far do we need to go with certain specifications like bot speeds in certain areas? Do we really need to achieve the actual original specification, or is something slower still enough to get the performance of the system? We've also used it to size the capacitors of the bots, as we're not using batteries but supercaps, and was important not to size them too small. And maybe one example that we saw in the simulation that's actually originally a little bit counterintuitive. So we realized that if the bots just go orthogonal on the decks, if they have to turn, they just go orthogonal, they stop, they turn, and they move on. That's the original idea, and there was an idea to increase the throughput of the bots through the decks by making those turns radiused. But it turned out that that wouldn't really help the actual performance of the system. So we were able to really cut the development efforts in that process and focus it on different things where the performance increase was larger than through the radius turns. So as we have this model and the first system gone live earlier this year, it's interesting to see where this whole technology will go in the future. And therefore, I will hand back to John to give you an impression of that.
All right. Thanks. So now that we have the robots, they're in pilot, they exist. We are certain that we can now automate a supermarket. So this is an animation that shows what the store could look like. It's a two-building structure. The store itself in this animation is only 17,000 square feet, which would be roughly the size of a Trader Joe's that has about 4,000 products for sale. But because we're leveraging vertical height, we can build all of the packaged goods. The center store effectively is all automated with an Alphabot. And so in this same footprint, we could very easily build a store that would be more typical of a 70 or 80,000 square foot store that might have 50 or 60,000 products in it. And so we're reducing the footprint of the store very dramatically, as well as the parking lot, because now people will spend much less time at the store because they're only shopping for their fresh goods, not their packaged goods. And many customers will choose to order everything in advance and either have it delivered to their home or pick it up. And so they're occupying a parking space for just a few minutes. And so this allows a very dramatic increase in sales and assortment combined with a dramatic reduction in footprint, total real estate costs. So this is the animation People come to the store only really because they want to either pick up their order or they want to shop the fresh market. They can order their packaged goods in the store. We can have screens and we can put that at ADL level for people who have trouble standing up. So we can serve all customers. The reason for bringing them to the store, the retailer wants to bring customers to the store because that's going to be their lowest cost of service and they can stimulate additional sales. You'll see a cooking demonstration in a bit. We want the store to stimulate people to be hungry and buy more food and get inspiration of what they want to buy. There's no checkout. You saw some ATM-looking machines. Those are checkout kiosks if you have to pay in cash or with a credit card. Otherwise, you pay on the phone. The phone becomes the shopping terminal to show what they're buying in real time. They can change their mind, whatever. So this is celebration food. This is experiential retail. This is customers. We're taking advantage of a very well-developed survival instinct of people want to eat. People love to eat, and so shopping in the fresh market is an exercise in planning what you're going to cook for dinner and providing for the family. So we're leveraging that, but people, they don't have to come. They can order everything if they want. The beauty of this model is that it serves the people that want to select their own fresh, as well as those who don't care and would rather have either a human being select it from the floor, or we can pre-pack the fresh and put it into the robotic system. So in this model, we would hand off on a conveyor. It'll actually be a little bit more refined. It'll be actually handing directly to a robot. But we encourage retailers to allow the customers to connect to the automation. So this is the same animation I just showed being put into effect in the store. The pickers won't be quite as exposed as this, but I think it's important to show customers how the system works and make that connection. The cool thing about the robot, because it can move vertically, we can let it leave the building and actually deliver to curbside. So we can actually present the tote to the customer and they can take the bags out of the tote. I want to extend now and use AnyLogic to model the store, all right? And so the agent-based capability of doing that is, I want to be able to model what customers do, what the store associates are doing. I want to build the store in virtual space before we actually build it in physical space. And the combination of different modalities in AnyLogic, I think, will lend itself very well. We're going to have to make our best guess how customers are going to behave, but by building in a feedback loop, we can refine and start testing what is the benefit on bot count if the retailer encourages more customers order in advance so we can pick their order before they get to the store and we don't need to be delivering that 3 or 4 average minute fulfillment. And so, getting into complex questions like how do we design the store, how do we lay out the store, I think those can be very effectively answered in simulation rather than real-world experimentation. Anyway, I think that's it, right? So thank you very much. Okay. Do we have time for questions?
Yeah. Are there any questions or? I like it.
Oh, let me just make one point. I want to make one point. Because it gets to our relationship with Walmart. We need to be very careful. This is our vision of future store. I don't want anybody to interpret that that's necessarily Walmart's vision. So we're not collaborating yet with Walmart on the Nova Store project, just on the Alphabot as a automated fulfillment. I think that's important to understand. Okay, any questions?
One question.
Yep.
Well, I can go first. I already have the mic. So, first of all, congratulations. I think this is a great project that you have. My name is Miguel Campos from Georgia Tech. We're also working like kind of large-scale simulation models. And there's a lot of things I find interesting, but I wanted to ask like 2 questions. I'm brand new in AnyLogic. This is like my first year working in AnyLogic. I've worked with simulations before. But I wanted to know, first of all, how the actual results of the implementation can be compared to those of the simulation. Because these are really interesting cases in which you build the model first, but then you went and implemented it. So I wanted to ask, like, how can you compare like the results you had before and after?
That's actually a pretty good question. So we started with a system that wasn't existent at that point. But I've been in very close contact to the MCS group, so the material control system, that are actually developing the bot logic or implementing the bot logic. So it's supposed to be pretty aligned with the actual system, but that's, to be honest, a point we still have to do to validate the simulation results to actual system behavior and system performance.
And very early on in the first project, Alert had very extensive Excel spreadsheets. So we use those as kind of our base case. Let's compare the model to the spreadsheet. We like to think that the model was more accurate than the spreadsheet, but it was a really good validation exercise because we at least had a ballpark idea of what these systems could do, and it was an opportunity for us to say, when the model is different, why is it different? Does that make sense? Would we expect that difference, given the difference between the Excel spreadsheets and the simulation model? So I think that's a pretty general exercise we go through a lot with systems that don't exist yet, is doing a side calculation of what you would expect and then trying to determine why the differences are there. Are they explainable? Who do you trust more, the Excel spreadsheet or the simulation model? Getting everybody in a room to discuss if everyone feels that the results of the model are valid.
Let me just say a couple of words. The system as it exists today in the real world is very, very close to what you saw in the animation. In fact, we like to talk about how we take animation to automation very well. And and part of that's because I'd been with Bill Fosnight, we'd been working on this for a long time. So we had already thought through the system design to a good deal. The decision support tool became very important, as Christian described, for making very specific design decisions. But the initial simulation tended to also validate the spreadsheet estimates pretty well, too, in terms of bot count. That was a critical one for the capital expenditure required. But my estimates initially were a bit low, but we had a contingency built in to allow for the uncertainty, and the simulations and now presumably actual results we'll be getting are pretty indicative or conform fairly well to the spreadsheet. So the tool has been tremendously useful, but it always helps to have a really well thought out system design before you start, so that made a big difference.
Thank you. Just another quick question. Maybe it's not like a smart question, but I don't know how to do it.
Yeah, that's right.
How did you connect the AnyLogic with the Excel? Like, you developed the add-in yourselves, or how? Yeah, that's an add-in that Mosum Tech uses. It's great for quick projects. You know, I love the private cloud and the custom user interface. And sometimes we do more complicated user interfaces for ongoing applications and multiple users. But in this case, that Excel add-in is something that we kind of have on our shelf that we can just grab and go. It's a AnyLogic template, a lot of VBA that's just been built up over the years with multiple people contributing and refining it. So I would highly recommend, whether it's Excel or anything else you use, just kind of building up your base of AnyLogic and reusable code that you can use from project to project. Thank you.
Yes. I would welcome a store like that, because the sort of the trend of the plus stores and the super stores, I mean, you're foot sore by the time you get in there, and then you've got a quarter-mile loop around the inside of the store to get all your shopping done. But there's so much of the grocery store business that's built on having a store that size and the manufacturers paying premium prices for certain locations and end caps. Can you just talk a little bit about like the business of how does this become more profitable, or is it like a niche location, let's say a downtown, which doesn't have a lot of space? Thank you.
Well, real estate is a problem anywhere, even in suburban locations. So being able to put smaller stores closer to customers is going to be beneficial. But I thought you were going to go to impulse buying. What about people just you lose that impulse if you don't have people walking around and seeing the shelves. But all of the interaction of the customer to the store now is digital, and so you still have the opportunity to stimulate incremental purchases, but it'll be digital, and you still have the option for incremental impulse buys in the store. But to my mind, impulse buying is a secondary decision. The decision the retailer needs to win first and foremost is that they come to their store. So if you have a better experience for customers, fundamentally, they will come to the store. The relationship with the manufacturer and the retailer remains the same effectively. I think it'll tend to put more of a focus of retailers on making money by selling to customers rather than taking money from manufacturers. But you still have the opportunity for virtual end caps, for presenting advertising and promotion to customers for a fee. So there'll still be some of that. I think it'll change the economics of retailing fundamentally very much in favor of the retailer of making the store a lot more profitable, of being able to, the common metric of sales per square foot is now going to be just a wholly different scale because we got so many fewer square feet and so much higher sales. So I think that all of the economics of retail get better. And once you automate the store, then it becomes much more straightforward to automate the supply chain that feeds the store. So we see a dramatic transformation in retail economics.
Excellent presentation. Alan Barnett from Golden Research Labs. We also are doing quite a bit of work in the retail space. I was just curious about the scope of the project. The other big wicked problem in retail is making sure you don't have avoidable shortages and surpluses. And I'm wondering whether that's going to be part of the scope in the future, or is it already in there to, testing new advanced algorithms to make sure that you don't get avoidable shortages and surpluses?
Well, the biggest cause for out of stocks and shortages on the shelf have to do with the uncertainty of the data. They just don't know what's on the shelf. And that's a serious problem in online because the retailer not knowing for certain what they can make sure that they can provide means that they're offering products for sale that they can't be guaranteed that they will have. And substitutions is the highest source of dissatisfaction for online customers. And so with our system, one of the side benefits is that we track every product by the item that goes in. So we have a real-time, nearly perfect inventory. And by making the entire supply chain a single machine, we can guarantee that when we commit an order to a customer that we can have it available when it's ready to pick.
And just a follow-up question, is it linked specifically now to Walmart, or are you also looking at other retailers? Because obviously this is a generic problem within the industry to solve.
Right, it is. It's a big world. We're focused on Walmart right now, but our vision is that this will become available to everybody.
Thank you, guys.
Thank you.